We'll get started. My name is Mustafa Mahamid, and I am with the University of Illinois at Chicago. Today, we'll talk about design of masonry structures. We'll cover material about the different components of a masonry structure and their specifications, because those are important in showing on the drawings. And we'll talk about the design methods, covering allowable stress design and strength design. And we'll cover mainly the design of walls, as it's the main element, the main masonry element that we typically design out of masonry. But additionally, we have also like lintels, which is part of the wall, but it's designed as a beam, as you will see. So we will have, so we'll try to have a break about halfway, maybe for 5 minutes, and then we'll continue after that. Okay, so looking at this figure here, so we have masonry elements. As you can see, they're all part of the wall. So we have masonry lintels, which is typically over an opening. We have masonry wall jamb, which is a vertical element adjacent to an opening. We have masonry pilaster, which is like a column, but it's an integrated part of the wall. And we have a masonry control joint, okay, to allow movements within the wall. So so when we design masonry structures, we have to consider all these that could be part of a wall. And sometimes we have some isolated elements, such as columns. That's possible too. So we have to design those as well, and those are also addressed in the code. Now, masonry is a structural material. It has been used as a structural material for a long time, before other materials were used in structures. So it's as old as the masonry itself. It was the dominant material in many far separated cultures, and then took a secondary role with the coming modern steel and concrete. So that's when masonry started to become less used as a main structural element. But still, until now, even in tall buildings, we do have some masonry elements, but they are secondary elements that are used for different purposes, not necessarily for supporting a main element in the structure, okay, such as a slab or the wall that's supporting slabs, or a beam that's supporting slabs. It has been neglected in spite of its image as a strong and durable material. Again, this is due to the presence of steel and concrete in the construction industry. And of course, as you know, we also have timber, which is also old relatively compared to steel and concrete, because it's a natural material and it has been used also over the years. So the world's largest office building was built in 1983. And it's one of the tallest load-bearing brick buildings, and it's in Chicago. And it's shown in this figure here. And the walls at the base, or the first floor, these walls here, they are 6 feet thick. Okay, so it's a load-bearing structure. It's masonry, and it's been known as an icon building for for masonry structures. Masonry has been used for a long time, but it's a vulnerable construction. So many masonry buildings have been destroyed during natural disasters, such as earthquakes and hurricanes and floods. Now, Many masonry buildings were built in the past just using the masonry itself without any reinforcement, such as what we do. It's different from what we do today. So therefore, as a material, it's a brittle material, so it does not have ductility to withstand, for example, earthquake loads. So therefore, during earthquakes, we see a lot of damage or collapse to masonry buildings. So these things have been learned over the years that, of course, we have to make some improvements to make these buildings stand. And that's why now, today we have the codes and the provisions that will cover some of the issues that were faced before, and which would allow also to would allow the structure to stand uh, some of the earthquakes. And again, that depends on the level of the detailed design that we provide to these structures. So here you can see these type of buildings are very common and have been standing for many years. This is a typical type of construction, in the U.S. that's made of masonry, and that's of course, clay masonry. Uh, so it's the whole building like that, and then the interior floors, it could be timber, could be steel, could be masonry walls with concrete floor, timber floors, etc. So this is very common. Uh, Now the question is, how durable are these buildings, and how strong are these buildings if they are exposed to new types of loads that were not designed for before. And as you know, codes change, right? So wind load calculations change due to the better knowledge that researchers have about how to calculate that, and to predict, of course, changes in the environment. And as you can see, the hurricanes and the tornadoes, that actually, some has been incorporated into the codes, and some actually are under research to come up with values that would cover these strong loading conditions and also seismic. So in the previous codes, some areas did not consider any seismic loads in the design. Now with the IBC, of course, for the last 20 years with the IBC, it depends, of course, in the location of the building and the importance of the building also, and on the soil conditions of the building. So, and a building that was not designed for any seismic load may be required to be designed for some seismic loads. So, so these are all these building types that are shown here. They are unreinforced masonry structures. So failure or damage to these buildings, it could happen due to extreme events. And we have reinforced masonry. So here, this is the Excalibur Hotel in Las Vegas. It's a reinforced masonry structure. Is the tallest structural masonry building. It's about 28 stories. The walls are massive, um, and it's reinforced concrete block. So we do have reinforcement and grout within the wall, and this is done using high lift grouting, which we will talk about that. So we have low lift grouting, which is up to 5 feet of the height of the wall, and then we have high lift grouting, so building levels and then apply the grout from the top. Okay, building envelope. This is used a lot actually in older buildings and in new buildings. So here we have an example of a building that is not old. It's a Colombian condominiums in Chicago. It's 48 stories. This building is not old. I used to walk by it every day during construction in the years of between 2000 and 2010. And you can see the exterior is all brick that's attached to the backing, which is a concrete block or concrete walls. as of course, as they exist, along the height of the building. Okay. Okay, pre-stress masonry, that's another type that exists actually. So concrete block is like, and even, clay masonry, they are weak in tension. So we need reinforcement. And to overcome the tension problem in these structures, we apply pre-stressing. So this is one of the applications that can be used. Here you can see the tendons and the couplers and the top anchorage and the bottom anchorage to the rebar that goes into the foundation. Okay, so we apply the force, the post-tension force from the top, and that will of course apply compressive force into the masonry. Okay, tension in the tendon, compression in the masonry, that will give us more capacity in the concrete block, and can support more loads in bending, and of course combined bending and axial loads. Here we have this is mortarless masonry block. Okay, so these units can be built without mortar, as you can see. So you can see the reinforcement also that's coming, that's coming from the base here, and so these units need to be grouted to make, of course, the reinforcement effective within the masonry concrete block. Okay. Here we have also the autoclaved aerated concrete masonry. This is also used in some areas, especially some of the warm areas, as it has good insulation between the outside, from the outside temperature. And typically it's light also in weight, which is good for our structures. So it's lighter, so it will result less dead load, which would result in, of course, lighter foundations, lighter seismic loads. Okay. In the structures that we design, we always have masonry with something else, right? So we have, for example, here in the picture, we have masonry walls, we have steel beam, we have could be like a header that will continue over an opening. We have a metal deck, concrete slab with reinforcement. So the wall is typically is the main element that we have, and it could serve different purposes. So could be a load bearing, could be non-load bearing, but it has to resist some lateral loads, or if it's non-load bearing. And here we have a gap between the bottom of the beam and the masonry wall. This is to allow deflections, between the deflections that are coming from the slab on the steel beam. But this is one example, but many other examples that could have precast concrete slabs supported directly by masonry walls, or supported by steel beams also, or supported by precast beams that are over openings, and then you have masonry walls continue after that. We also have free-form masonry. So as you can see in the photos, some of these actually are recent, where they built nice structures using masonry, and will give it, of course, a massive and historical look. So architects prefer that, and that can be of course that can be done using masonry. So you can see the heights and the spans. So this will require, of course, good engineering to make this happen, stand, and also durable, and also design all joints to allow expansion, contraction, etc. Okay. Okay, for the structural design, so things started in the design of masonry. So it's been used, for thousands of years. But if from an engineering standpoint, there in the modern era, there was an empirical design that was developed, and that was used in the first half of the 20th century. I mean, after that, code started to be developed, and also masonry associations also started to do research, and come up with specifications for engineers, guidelines for engineers on how to design certain things. So we have the BIA, that's the Brick Industry Association. It was established in 1966, and we have the NCMA, the National Concrete Masonry Association, in 1970. Those developed standards for structural design for the for the brick and blocks. Okay, then we have codes that um, were developed jointly by the Masonry Society, TMS, by ACI, the American Concrete Institute, and by ASCE, the American Society of Civil Engineers. And we have codes that first started in the Uniform Building Code, the 1985. That was Chapter 24, that covered masonry, and then that also was used in other versions that came after that in the UBC, and now we have it in the 2018 International Building Code. It's a little bit more expanded than it was before. And so this is the code that you see in the photo here. Now we have the most recent one is the 2016, which is a nice document that covers many aspects of structural design and specifications for concrete and clay masonry. Now, classifications of modern masonry covers we have engineered construction versus non-engineered construction, and structural masonry versus non-structural masonry. So we do have non-structural masonry in the building. Those are architectural, typically, uh, like partition walls, for example. Then we have reinforced versus unreinforced. We have partially grouted or fully grouted versus ungrouted. Clay unit masonry versus concrete unit masonry. Solid units, hollow units. Single width, multiple width. Cavity walls, composite walls. Bearing walls, non-load bearing walls or non-bearing walls. Running bond, stack bond. And then working stress design, strength design. So these are, of course, important terminology to know about masonry. So we know what we are designing based on the function of each type. For the clay masonry, which you saw in the photos before, that's not block, that's not a concrete block that we typically use. These are surface clays that are used for building envelope. Those are made of shales. It's the fine grained clastic sedimentary rock composed of mud. For fire clays, we have iron oxides, hydrated silica of alumina, and there were miscellaneous impurities: calcium and magnesium, sodium, titanium, and potassium. So, there's an ASTM C270, that's a standard specification for building brick, that shows all these components and explains about the different components and what's the function of each one of them. Now, if you are using that, you have to specify it. And if it's used for the building envelope, then the architect has to specify it. So that's the specification for it. It's ASTM C270. And that's it's a technical BIA tech note number 9. Okay, so you can go actually to the BIA website and to the NCMA website, and there are many technical notes. I suggest you download them. They are for free, and have them in your library, your digital library, because you would need many of the information there for specifying, material, and also for design. So some technical notes actually show design procedures that you can use in your calculations. Okay. Now, engineered properties of clay units. Clay units, they have a lot of engineering properties such as absorption, durability, volume change, compressive strength, flexural strength, thermal conductivity, acoustics, fire resistance, and elastic modulus. So those are in Tech Note 3A of the BIA. So they have all the material properties for whatever you use. Okay, and that's what it is. So Technical Note 3A. And then we have physical characteristics of clay units, which covers color, texture, form, size, and dimensional tolerances. That's in Tech Note 3B. That's section properties, and that's what it is. Okay. And so it shows the different types here. So it shows, for example, the top, we can see, okay, we have the cell, we have the webs of it, and then we have the solid face shell, okay? And then we have the cell or core, and then we have the end shell or end web, okay? And then the other ones, are shown below. So based on that, you can specify which type is needed based on the properties that was discussed before. It doesn't have to be only structural properties, but there are other things that architects would be interested in. Okay, so in the same tech note, you have like nominal width of the units, so 3 or 4 inches, 6 inches, up to 12 inches. And then we have the minimum solid face shell thickness. We have minimum core or double face shell thickness, and minimum end shell or end web thicknesses. Now, these things are important if you have that ordered, to be on the site, then making sure that what was ordered is according to the specifications. So these are the specifications. So if it's a 4-inch nominal width brink, that's what you should have. Okay, so minimum end shell thickness is 3/4 of an inch. Minimum solid face shell is 3/4 of an inch. Okay, so that's why these are important. The unit compressive strength ranges for the brick in North America between 3,000 to 30,000 psi. The nominal strength that is available typically in the market, or the one that's used, is 8,000 to 15,000. So that's very, as you can see, if you think of, for example, concrete, that's a lot. That's very strong. So they can support actually high compressive stresses. That's why you see them, in walls, and they have been standing for many years. Now, the modulus of elasticity of clay masonry is between 1,400 to 5,000 psi. We would be interested in the modulus of rupture. Okay, and that can be determined using, of course, a simple test. So you have that information in the technical notes, but for the modulus of rupture, it's very simple, determined using the moment divided by the elastic section modulus of the material. Coefficient of thermal expansion, moisture expansion, freezing expansion. These things are important because we need to calculate expansion joints. We need to specify those. We need to show them on the drawings, also on elevations. That's the correct design. Otherwise, after some time, cracks will start in the masonry walls, and then people have to deal with it. They have to do the repairs. But if we design the expansion joints properly, the issues will be, of course, less. So these typically you have to calculate thermal expansion using the delta T that's used in that area, and you have to calculate the moisture expansion also, and then using the freezing expansion also. So you have to look at the different season and calculate that and provide whatever is is needed for the expansion joint. Okay, so those values are given the code, in the TMS 402, and in the first chapter, as you can see. Okay, and typically, if you have not taken the PE exam or the ASCE exam, you will see some questions about calculation of expansion joints or control joints in the case of concrete masonry. So for concrete masonry, the ASTM specification for it is C90. This is something that typically we show on the drawings. So this shows the dimensions, for the masonry block that you are using. So typically, we will use, for example, if it's an 8-inch wall, we'll use 8 by 8 by 16. These are nominal dimensions. Okay, so we have the width, the length, and the height. Now the actual dimensions are 758, 758, 1558. So they are 3/8 less than the nominal. That's easy to calculate. Okay, so in design, that's what we need to use. So we have to use the actual dimensions, and of course, we have a tolerance of 1/8 of an inch for the differences, if it's different, of course, from these exact dimensions. Okay, from its name, it's concrete masonry. So the making of the concrete blocks is made from the same components of concrete material. So we have Portland cement, we have pozzolans, aggregate, other admixtures such as air entrainment, pigment, water, and water repellents. Aggregate could be normal weight aggregate, could be lightweight aggregate, and typically, for masonry, we rarely use normal weight, but typically we use medium weight to lightweight for structural applications. Okay, so here we have the references. That's from the NCMA Tech Note 1 to 1F. So we have many specifications for concrete masonry that we need for. So in the drawings, typically we specify the specifications, but in the specification book, we have to be more specific about what should be used. And then we have the NCMA Tech Note 18.2, that's sampling and testing of concrete masonry. Okay. So here, this is from chapter 4 of the code, the TMS 402 or ACI 530. So we have the elastic modulus of the different material. We have for the steel, the one that 29 million PSI. And then the modulus of elasticity of the masonry, 700 times F prime M for clay masonry. F prime M is the compressive strength of the masonry. Okay, just like F prime C in concrete, here we have F prime M. And then for concrete masonry, it's 900 F prime M. Okay, you will use this a lot. Okay, so that's the modulus of elasticity. Just like concrete, it depends on the strength of the material. Compressive strength, it's the same here for masonry. And then we have also the modulus of rigidity for clay masonry and concrete masonry. It's 0.4 of the modulus of elasticity. Okay, so that's easy to determine. Once you have the E sub M, then you have E sub V. Okay, so here again we have coefficient of thermal expansion in chapter 4. We have coefficient of moisture expansion. You have coefficient of shrinkage. Now the shrinkage is used for concrete masonry, right? Because it's concrete, it shrinks. It's made from the same material. It does not happen in clay masonry. Okay. Now mortar. Now mortar is an important component of masonry. So masonry is not like steel or concrete. In a masonry structure, we have, or masonry elements, we have different components. We have the blocks, the masonry blocks, which could be concrete or clay. So we have the units, and then we have the mortar, which we use to build these units together. And then if it's reinforced, we have reinforcement and grout with it. So that's the composition of a masonry element, okay? So we have different types. So as you can see here in the figure, so we have unit, mortar, unit, okay? Now we have three types that are typically used for structural applications. We have type N, we have type S, and type M. The ASTM specification is C270. So this is something that you also need to specify as a structural engineer. Okay, the specification for the mortar that to be used in the masonry units. Okay, now whether which type of mortar we need to use from these three types, that of course depends on some of the applications, but typically S is appropriate for many of the structural applications. N is acceptable for some applications, but not for some, such as seismic applications. And M is a little bit is actually less used. It has more strength, but it's less used because it's a little bit more expensive, and it requires also it requires some work to just maintain it during building to have its strength and the right contents of the material while building the masonry. So here you have different ASTM standards for the components that are used in the mortar, and here you have the ingredients for or the proportions of the ingredients that are used for each type of mortar. So here you see the mason work, right? That's mason work. So the capital letters indicate the different types of mortar. So we have the M, the S, the N, the O, and the K. M is the strongest and K is the weakest. And as I said before, for structural application, we use M, S, and N, okay? That we have to have a certain compressive strength for the masonry, of course. So we do, those could be done in the field. Of course, preparing the cubes or the cylinders, like 2-inch cubes or 2-inch cylinders, and then those need to be tested. But that's these are the dimensions that are required for that. So here you can see that. So you can see the rebars, and then you can see here the mortar where it's used at the joints. Okay, so here as you can see, the mortar is used between the joints, but whether it's used only at the at the edges for the face shell here, or whether it's used across the web also. That's an important actually point, and something to look for if you are for example a field engineer or a designer even visiting the site, because sometimes this is overlooked using a mortar in between, and then some tests have shown the difference actually in strength if it's face shell bedded or if it's fully bedded. Okay, so fully bedded, that you have mortar all over, or face shell bedded if the mortar is just on the outside. Okay, so here you have property requirements for mortars according to ASTM C270. So for M, compressive strength is 2500 psi. So that's a requirement to have a type M, because eventually the type of the mortar will decide on the F prime M in the compressive strength of the masonry. If it's S is 1800 psi, and then water retention 75%, and then maximum air content is 12%, etc. Okay. Okay, grouting masonry. So that's another component. So grout placement methods could be low lift. So that's, we mentioned this at the very beginning when we showed the Excalibur hotel structure. Grout is placed and consolidated as masonry is constructed. Maximum grout height is 5 feet, maximum every 5 feet. The high lifting, this is typically used in multi-story. So grout is placed after a story height is constructed. and then vibration is needed. So you have a full story, you grout it, and then you vibrate it to make sure the grout has reached to the bottom. Typically, we have clean out holes at the bottom, just to make sure that the grout has reached below, and so that the especially where we have rebars for the reinforcement, because if there's no grout, the rebar will not be effective at all. So we have to make sure that that's done. And actually, many tests in the field, unfortunately, just using a hammer, looking at the grout at those where the cells where we have rebar, and we discover that the grout did not reach there. So that's an important thing that need to be checked. So for this, NCMA Tech Note 3-2, grouting for concrete masonry wall. Just, there's a lot of good information about grouting there. That's the technical note. Okay. And that's grouting. So you can see where we have the rebar. This is it looks like this is low left grout. So you can see where we have the rebar, we fill that with grout. Okay. And here you have the proportions for the grout mix, using the Portland cement, fine aggregate, coarse aggregate, and then hydrated lime. Okay. We have also Tech Note 9.4, that's a grout for concrete masonry. That's another one, so that you can use. So 9. So we have 3.2 and we have 9.4 also for the mix of the grout. Oh, and then we have the reinforcing steel. Okay, the steel could be what we know from concrete. Number 3 to we have number 3 to number 18, but typically in masonry we use typically number 3 to number 11, but beyond number 9 is not recommended. So up to number 9 is okay, and there's actually a requirement that the rebar diameter should not exceed 1/8 of the wall thickness. 1/8 of the wall thickness should not exceed that. But typically, to have reasonable bars and that can be grouted, can be effective, up to number 9 in masonry walls. Whether grade 40 or 60 can be used. Okay, these are the ASTM specifications. Typically, these days we use 60. That's what's available in the market. And we have joint reinforcement. Okay, joint reinforcement, the ASTM specification for that is A951. That's a ladder reinforcement. It looks like the ladder. And as you can see, this is looking from the top. Or you have truss type reinforcement. Okay, we call this joint reinforcement, which is it's used to control, of course, a cracking in the wall, and also it could be used as shear reinforcement. Okay, so if you have a shear force that's horizontal on the wall, in a shear wall, in a masonry shear wall, and masonry walls are used a lot for that purpose as shear walls. So this reinforcement can be used for that purpose. So in NCMA Tech Note 12.2b, you can find the different types of joint reinforcement, and that's from that technical note. Okay, here is a photo for that. Okay, now we have this Tech Note 1 to 1F. We did talk about this before. This shows the ASTM specifications for concrete masonry units. Here we have load-bearing concrete units, non-load-bearing concrete units. So these are the ASTM specifications that we need to use typically for structural applications. The non-load bearing, it may not be supporting a load that's coming from the top, but it could be supporting lateral load if it's an exterior wall, such as a window, okay? And here you have, for example, ASTM C270, that's minimum face shell thickness and web requirements for hollow units. Remember, we talked about this for the brick, okay, for the clay brick. Here, this is for the concrete block. So there are also minimum requirements just to make sure that what was delivered to the site from the plant meets the specifications that we have, okay? So here you see the gross area, that's the shaded area, and here you see the net area. Okay, that's also the shaded area. So typically we are interested in the net area because that's what we typically will have. We will not have the whole masonry wall fully grouted, so we can consider the gross area. Typically we have it partially grouted, so or hollow. So we are typically interested in the net area. And also to decide on F prime M, we need the net area of the unit, that's the shaded area, with the with the mortar strength. That will give us what's F prime M, as we will see, okay? So bond patterns. So here we have different bond patterns. Maybe you have seen some of these. So those are listed actually in the, in some of the references and in the code also, with some of the tolerances. So it depends on where these came from and where this was used architecturally, before. The mortar joint types. So here you have different types that, that are related to the finish, how the finish is done. And this is not only related to the finish, but also related to the maintenance of the wall and the behavior of the water in the wall. If it, and how can, if the water again can penetrate through these joints or not. And typically that's one of the main concerns that we have, is water in masonry structures, which causes a lot of damage typically. Okay, masonry organizations. So here, at the beginning we talked about the BIA, the Brick Masonry Association, and the NCMA, but there are other organizations, and here you have their websites. So you can refer for whatever technical notes that you may need or any other information. Okay. Now, for the design, masonry can be designed using strength design similar to concrete, and for those we need to use factored loads. Okay, and this is again similar to concrete. Or if we are designing using ASD, allowable stress design, or working stress design as it's referred to in some of the documents, we have to use unfactored loads, or this set of load combination, which are actually listed in IBC and listed in ASCE 7. Okay, so for the compressive strength of masonry, so we have this table from the code that shows the compressive strength of masonry based on the compressive strength of clay masonry and the type of mortar. Okay, so this depends on the net area. Remember, we talked about the net area compressive strength of clay masonry unit. Okay, and here you have the type of mortar. Okay, N or S or M. So with whatever net area we have for the unit, plus whatever type of mortar we have, those have different strengths. Okay, that will give us the net area compressive strength of clay masonry that we need to use in our design. Okay, so here you look at, for example, net compressive area of a unit. So for, let's say 4,150. 4,450 with type N, we will get 1,500 PSI. Okay, so that's how this works. And then we have the same thing for the concrete masonry. So here, net area compressive strength of concrete masonry unit. So if that is, for example, 2,650 PSI with type N, that gives us 2,000 PSI. Okay. Now, these days, typically engineers specify 1,500 PSI in the drawings. Now, this is really underestimating the strength of the masonry. As you can see here from this table, with type N, we can get 1,700. I mean, easily, you can easily, these days, you can easily get 2,500 PSI F prime M with the appropriate type of mortar. Okay, many prisms have been tested. You can easily get 2,500 PSI. So you should take advantage of that and design masonry structures, based on that. And prism testing. So you can determine F prime M from this table in the code, or you can do prism testing, which is not difficult. It's 2 blocks with mortar, the type of mortar that you have based on the ingredients that we discussed before, and then subjected to a compressive load and do that. So those could be done even during construction. It's not difficult to build, and they can be done on site, and they can put in plastic bags, shipped to a lab and test. And there are, by the way, specifications for those. Okay, and they have been done on many projects before. Okay, now looking at the design, so we'll start with unreinforced masonry walls. So in walls, as you can see in the figure to the right, walls could support floor or roof loads, could support in-plane shear walls, could support out-of-plane transverse loads, and those are for example, from wind loads. So they can resist axial loads, they can resist shear loads, they can resist also bending. So we have to design for all these possible scenarios depending on what we have, okay? And also could be gravity load only with eccentricity. So that will produce bending also, okay? So here you have some of the details that are mostly related to brick in this case. Again, those are taken from the technical notes. Many of us, of course, probably would do some repairs on existing buildings. This is many companies do that work. So you have to understand, how maybe there are no drawings, but you'll get an idea about how these walls actually supported the floor. So different, scenarios here. Again, this is brick, and brick with precast. That's, precast on the other direction. That's not the span direction. It could be steel joists, okay? So for unreinforced masonry, typically we have Chapter 8 will cover all the provisions that we need for the design of masonry structures. Chapter 9 covers reinforced masonry, okay? So in this section, what we need is the design assumptions. So strain in masonry is directly proportional to the distance from the neutral axis. Flexural tensile stresses in masonry directly proportional to the strain. Flexural compressive stresses in combination with axial compressive stresses in masonry directly proportional to the strain. And the stress in reinforcement, if present, are neglected when determining the resistance of the masonry to design loads. So again, this is unreinforced, so we neglect the reinforcement. Again, this is simple. Basically, using a linear elastic stress distribution, the stresses are proportional to each other, and then we can determine the relationships between them based on what's required. So here in this section, we have axial and flexural compression. Okay, So and again, that's what we typically have in walls. Typically, we design walls that the minimum axial load on the wall would be its self-weight. That's the minimum. And then we have, of course, bending on it, which could be due to wind, or if it's a load-bearing wall, could be from eccentricity, or could be wind load if it's on the outside. If it's an outside the wall. So the interaction equation for compression is F sub A. F is a small letter. This is the actual, the calculated axial stress, divided by F sub A. F is capital here. That's the axial capacity, okay? Plus F sub B, F small is the actual bending stress. And then capital F sub B, that's the bending capacity. This has to be less or equal than 1. At the same time, the axial load has to be less or equal than the critical buckling load divided by 4. Okay, so that's for compression. Now, below you will see F sub A, how it's calculated. It depends on F prime M, the compressive strength, and also depends on H over R. H over R is the slenderness of the wall, the height divided by its radius of gyration. Okay, so what's in brackets here, that's the slenderness effect that's taken into consideration in the axial capacity. Okay, that's if H over R is less than 99. If it's more than 99, we use the equation below, equation dash 17. The bending capacity is 1/3 of F prime M. Okay, 1/3 of F prime M. Okay, and here we have that's the P sub E, that's the critical buckling load. And again, it depends on E sub M, the modulus of elasticity of the masonry, the net moment of inertia, I sub N, H the height of the wall, E is the eccentricity, and R is the radius of gyration. Here you have the buckling curve, which you know from whether it's for masonry or for concrete or for steel. It's similar in its shape. The values are different. Okay, so it depends on either H over T, the thickness of the wall, or H over R. So you have two scales here in the x-axis. So you can see here, if it's to the left of this line, this vertical line here, that's close to 30 or 99. So we're dealing with H over R in the equation, so it's 99, right? 99. So to the left of that, the failure would be mostly material failure. To the right of that, it would be a stability failure due to its slenderness. Okay. Now, the F sub A, the calculated actual stress is equal to, this is simple. So we looked at the capacities here, right? These are the capacities. Now, the calculated stresses is F sub A is the load divided by the net area. It's very simple. The strength of material calculations, okay? Now, the net area, the net moment of inertia are, so remember, these walls could be grouted, could be partially grouted, could be hollow. So the best way to get their properties is using the NCMA tick note 14.1b. That here it is. Okay, so this for different sizes of the masonry wall. This is 8-inch single width wall. You have 1/4 inch face shell thickness. If it's a hollow unit, there's no grout. The mortar is only at the face shell. A net is this. That's an inch square per foot of length. The net moment of inertia is this, and the section modulus is this. Okay, so this is the net cross-section properties, and this is the average cross-section properties. Usually we use the net cross-section properties. Okay, so this you can obtain from the technical notes. Okay. Okay, for bearing walls, As you can see here, so we may have precast sitting on these walls. And we may have steel beams sitting in these walls. We may have timber, sitting on these walls. Now, typically, for bearing walls, the load is not. It's hard to place the load where it's a reaction of, for example, here. Sorry, here. So you have for example, this precast plank. Its reaction be exactly at the center line of the wall. You can see here we have rebars going up from the wall. Those are at the center. Those are at the center. Okay, so it's hard to place that at the center. So typically we do have eccentricity on the wall. Okay, so the axial load is P over A. That goes through that's one, of course, one calculation that we have to make. And then due to the eccentricity, we have a moment. So that's MC over I or M over S. So this will add compression to one side and we'll have tension on the other side. Okay, so as you can see here, we have FA plus FB. Here we have minus FA plus FB. Okay, so here we have tension plus the bending stress. I'm sorry, we have axial load plus the bending stress. And here we have both in compression. Okay, you have one tension, one compression. Here you have both in compression. So we have to check whatever we have and of course compare those with the allowable limits that we discussed before, and some that we will discuss also that are related to tension. And here they are. So if the limiting, if the stresses are, for example, in this case, F sub A plus F sub B, that's both compression, then we have to check this equation if it's satisfied or not. Okay. Now, for the other side, we have to see if we have tension or not. So in this case, it looks like we do have tension. That has to be compared with capital F sub T. That's the allowable tension stress in the masonry. Okay, that's allowable tensile stress in the masonry, F sub T, and this is given in this table in the TMS. Okay, so this table depends on what type of cement has been used in the mortar. So you have mortar types here. So you have Portland cement or lime or mortar cement. Here you have mortar cement or air entrained Portland cement or lime. So whether it's type MS or N, okay, for each type. And now the direction of the flexural tensile stresses and masonry type. Okay, so whether it's normal to the bed joint. Okay, the bed joint, that's where the mortar. So the stresses are normal to that joint. So for example, going here, right? So these are the stresses. If this is the mortar point, the mortar joint here, so are the stresses normal to it or parallel to it? So in this case, they are normal to it. So normal to bed joint, is it a solid unit? Then you use these values. This is in PSI, in parentheses in kilopascal. Okay, so 53 PSI for type S. Okay, if it's a hollow unit, then we have, is it ungrouted or is it fully grouted? So solid unit is just like a full block. There's no holes in it. But if it's a hollow unit, which is common, which is the one that's common actually, we have ungrouted, we have fully grouted. And then depending on the type of S and the type of mortar, we can determine what is F sub T, and then compare it with that. This slide shows you the flexural tension stresses, for example, here, normal to bed joint, okay? And this is flexural tensile stresses parallel to bed joint, okay? So that's how you distinguish between both cases, okay? So now let's look at if we have, for example, unreinforced masonry shear wall. So this is something like this. That's common. So we have lateral loads at each level, H1, H2, H3, etc. We have also axial loads, P1, P2, P3. We have diagonal. We have diagonal tension cracks that may happen in a shear wall due to for the shear forces that are applied to it. So the maximum load is at the first story, so this may happen here. And then we have flexural compression cracks. This is due to the overturning moment, okay, from H1 times capital H times small h, that gives us the moment. And then we have the flexural tension cracks. That's also from the other from due to the moment from the other side of the wall. So the total axial load is the summation of the of the axial loads from all the stories. The total shear is the summation of the H horizontal forces from all the stories, and the overturning moment M is the summation of H capital H sub I multiplied by small h sub I. Okay. So the design criteria for this, so we need to check the allowable flexural tensile stresses. We have a moment here, right? So this side, the left-hand side is tension. So we need to make sure that this is satisfactory. Okay. If not, then we have to do something else. If T is given in the table that we just discussed. Now for the other side, for here the compression. For the compression side here to the right-hand side, that is checked using this equation that we discussed before, combination of axial and bending in compression, okay? And we need to check also the shear stresses, right? This is a shear wall. So we have to check that, the shear VQ divided by the net moment of inertia divided by B. This is less or equal than the allowable shear stress, and the allowable shear stress is given here, section 8.2.6. So it should be for unreinforced masonry if we shall not exceed the lesser of what's shown here. Okay, typically we'll go with 1.5 f by square root f prime m and 120 psi, and then depending on whether we have a running bond, stack bond, like we showed before, the values may change. Okay, so that's where this is given actually in the code. Okay, that's where these things are. Okay, and how do we calculate the applied shear stress? So the applied shear stress, it's a rectangular section, so we have this parabolic stress distribution that we know from strength of material. Now the average stress is V over the net area, so that's 2/3 of the maximum, right? 2/3 of the maximum. Therefore, for a rectangular cross section, like we learned in strength of material, we have 3/2 V divided by A net. So that's how we calculate the small f. Okay, instead of using VQ over IB, so we can just use that and then compare it with the F sub V, which is shown in this section here. Okay. Okay, possible shear crack modes, cracking modes in masonry walls are shown like this. So typically it's diagonal. Sometimes you may have horizontal, but this will be due to small vertical forces. But if you have vertical axial loads that are coming in the wall, most probably you will not have failure in the mortar as shown here. Okay. Okay, so this is a simple example that gives you an idea with numbers of what we have. So this is 6 foot 8 inches. The height is 9 feet 4 inches. We have, the H forces are shown here. And then the axial force 5,000 pounds. That's a dead load. 8-inch CMU wall with face shell bedding block. So the strength of the block is 2,800 psi. That's the block. Okay, the net area for the net area of the block. And then it's type N mortar. So this is the wall. It's 80 inches. So it's face shell bedding. If it's face shell bedding, we can calculate the net area. It's 1.25. That's the shell. Type 2. That's 2.5 inches multiplied by 80 inches. That's the length. So 200 inch square. The section modulus 2.5, 80 square divided by 6, right, for a rectangular section. And then the radius of gyration is the square root of I divided by R. So it's 2.84. And also you can go to the technical note and get these values, okay, as we discussed before. The H is 112 inch and H over R is 39.4. So we have all that. So now here, the net area compressive strength is 2800 psi. So that is between 2650 for type N. That's what we have. It's between 2650 and 3400 psi. So that will give me something in between for F prime M between 2000 psi and or 2250 psi. Okay. Now VB is equal to 2H. So we don't know what is we don't know what's the maximum load that can be applied to this wall. Okay. So VB is 2H, and then MB we can find that it's a function of H. That's the overturning moment. It's H times 9.33 plus H times 2.2 times 9.33 times 12. So this comes to be 335 H. Okay, if we divide that by 2, we have 168 VB, the base shear, okay? And if we can calculate the axial load, 2 times 5,000, we have twice 5,000, divided by the area, 200 inch square, we have 50 PSI without the self-weight. And then the bending moment is M over S. So 168 VB divided by the section modulus, 2667 inch cube. That's 0.063 VB. Okay, so now the base shear is unknown, so H is unknown. So we can, based on the allowable stresses that we have, we can calculate what is the maximum allowable load. So according to the codes, minus FA plus FB is 25. So 25 is coming from here. This is 25. Okay, that's 25. It's type N, a hollow unit, ungrouted. Okay, normal to bed joint. Okay, the stresses are normal to the bed joint. Okay, so the 25 is coming from here. So from this, we can determine VB, it's equal to 1190 pounds. Check compressive stresses using this equation now. So we know FA 50, capital FA is calculated from here. We know all the information. Plus 0.063, this is coming from F sub B here calculated, divided by 667, that's F prime M divided by 3. Okay, so we have VB 9,600 pounds compared to, based on compressive stresses, based on tension 1190. So this one governed. This is the maximum load that we can apply. Okay, so that's for the unreinforced masonry. So now we'll start with the reinforced masonry. So the allowable stresses, so for allowable stress design, we use this set of load combination. It's the same concept. The only difference here is that we use reinforcement in the reinforced masonry. So this can be designed also using ASD, allowable stress design, or strength design. If we are using ASD, we have to use this set of load combination. So according to this, the strain distribution, of course, is linear elastic. So we have epsilon M, that's the strain in the masonry. Epsilon S, that's the strain of the rebar, which is located at a certain distance here, D from the compressive face, and typically that is in the middle of the unit. In the stresses, the compressive stress, you can see it's linear. This is an allowable stress design, okay, which we are not familiar with for concrete and steel and masonry. Okay, so we need to calculate the area of that rectangle. That will give me the compressive force, and then the tension force is the area of steel times the stress in the steel, F sub S. It's not Fy, it's not the yield. We don't know if the steel is going to yield or not. Okay, So N is the modular ratio between the steel and the masonry. See, the modulus of elasticity for the masonry is 900 times F prime M. That's depends on the strength of the material. So now, using this free body diagram and the concept of the stress distribution, allowable stress design, we can calculate what is the resistance of this element. So take moment about 1, find the moment. That will give you what you have here in terms of the moment resistance. So some of the assumptions here: plane section remains plane, neglect all masonry in tension, stress-strain relationships are linear, compression, stress-strain for steel are linear. We talked about that, and it's obvious from the stress distribution. Perfect bond between masonry and grout, and then the masonry units and grouts have the same properties. So we assume that the grout and the masonry units have the same property because we assume it's one block. So from assumption number 5, we have the strain in the steel equals the strain in the masonry. From assumptions 3 and 4, we have the stress ratio, the stress in steel divided by its modulus of elasticity, and the stress in masonry divided by its modulus of elasticity. So it gives me a relationship to convert one material into another. So FSI is equal the modular ratio N times the stress in the masonry. From geometry of the stress distribution, we can determine this relationship. Now D is this depth here from the compression phase to the rebar, and then we have KD, that's the depth to the neutral axis. Okay, so and we need to find that, of course. So we have this relationship, okay, and then from this we can find what is the stress in the steel, because it's not the steel does not yield in this case. So we can find the value from this equation. Okay, from equilibrium, tension equal compression, we can equate the stresses. Okay, the area of steel is equal to the point the reinforcement ratio times BD, like concrete, and then we can substitute that for in the equation, and we will have this relationship. Now, further simplifications, we have K over 2 equals to this relationship. And then we have this equation, K squared plus 2 rho NK minus 2 times rho N equals 0. So you need to find this here, because this will give you the K value. Everything is known. If you know the K value, then you know what is the depth of the neutral axis, then you can find everything, okay? So from once we know K, we can find, the moment, of course. Take moment about C sub M equals 0, the centroid of the masonry forces. So that's AS times FS times JD. JD is the distance between these two forces, T and C. Okay. So if you substitute for AS rho times BD, then here we have JD is equal to D minus KD over 3. Okay, this is 1/3 to the which is the centroid of the triangle. So J is equal 1 minus K over 3. So the first thing you do, you find K, then you find J from that equation. Then you can find the moment resistance for the cross section based on this. Okay. If F sub S is equal to the allowable F sub S, capital F sub S, which is given here, then the moment capacity is limited by the reinforcement. Okay, if it's not, then it's limited by the masonry. So allowable reinforcement tensile stress, according to ASD section 8.3.3, is 20 KSI for grade 40 or 50, and 32 for grade 60. If it's wire joint reinforcement, it's 30 KSI. Now, if you take a moment about the steel, Then we have the moment that's governed, controlled by the masonry. So 0.5 F prime M, oh, sorry, Fm, which is the strain in the masonry, the stress in the masonry, times B, that's the width, K, D, the depth, JD, or if, you can use this with the D square instead of the two Ds, okay? And if the stress in the masonry is equal to the allowable bending stress, then the moment capacity is controlled or limited by the masonry, okay? So basically you need to check M sub M and M sub S, okay, and then use the smaller one for the capacity of your section, okay. So for balanced conditions, okay, well, I guess let's take a break here. We're about halfway, so let's take a break here, and we'll resume in let's say 5 minutes. Faisal. Okay, let's continue. So here we have an example, which is to look at the balance condition. I mean, the example is related to finding the stresses using in the stress distribution, then find the reinforcement ratio from that. So it gives us the balance condition in the balance condition and the raw balance, the reinforcement ratio that we need to determine if the steel controls or if the masonry controls. So here we have to determine the ratio of reinforcement that will result in balanced condition per MSJC, that's the masonry code, given F prime M 2000 and grade 60 reinforcement. So if sub B is given 667 for 2000 psi, E sub M is 1800 ksi, the steel is 29,000 ksi, the allowable steel stress 32 ksi, and then N is ES over EM, that's 16.1. That's the modular ratio. So we have a raw balance, we just substitute everything here, assuming that the allowable stress. So what's the balance condition first? I mean, just to refresh your memory, maybe from reinforced concrete, the balanced condition is the condition where the stresses in the masonry, the maximum stress, the allowable stresses in masonry and in the steel are reached at the same time. That's the balance condition. So using that in the strain diagram, we can determine that reinforcement ratio that will give us the stresses in the masonry and in the steel at the same time. Okay. So based on what we discussed so far, so you have this flow chart. It gives you the procedure of how to determine or how to calculate stresses or how to design a reinforced member using the allowable stress design method. So you having the modular ratio, find the K value, and then find the J value, and then find F sub B, and then find F sub S, etc. So it's very organized, very simple to follow. Okay, here this chart is for the design of singular reinforced members using allowable stress design. The same thing. So here we have KD. So you can calculate the depth based on the given information. This is here, in this case, you have the load is given, you have the axial load is given, you have the allowable stress is given, okay? So you can determine what is KD here, and then you can determine if K is greater than K balance. K balance depends on the modular ratio N and the allowable stresses, okay? From that, you can calculate the required steel area, okay? And if of course, if K is greater than K balance, which is, the case that we need typically, so we can find it, here. If K is less than K balance, then in that case, the steel will control. Then we can find it from here. So these two flow charts allow you follow the design process easily. Okay. So here, okay, we can design a beam, which is a lintel in a masonry wall. That has a moment 320 kip inch. Prisms have been tested. F prime M is 2000 psi, and the grade 60 reinforcement is it's an 8-inch CMU wall. So from a previous example, we have the balance condition for these data is 0.26%. So having 60 KSI steel, having F prime M for the masonry. So these are the material properties, and the balance condition depends on the material properties. So that's why it's the same, because you were using that. Estimate rho to slightly be lower than raw balance. That's the preferred condition. So it's under reinforced, right? It's the same concept as in reinforced concrete. So we want it to be under reinforced, not over reinforced. So choose rho less than this. Okay. So we use 0.2%. So solve for K. I remember this equation. So we have K is 0.224, J is 1 minus K over 3, solve for BD square, so we can determine the dimensions of the section. So BD square is M, the moment, divided by, so we're given the moment, divided by rho J sub F times F sub S. So we have BD square is 5405 inch cube. So we can assume one, find the other, but we are given it's an 8-inch CMU wall. This means that we have one dimension, so we can easily find the other. So if it's an 8-inch CMU wall, then B is 7.63, okay? So D is 5405, 7.63 square root, that's 26.6, okay? So that's the total depth of that's the required depth of that. So we can now, this is the minimum, so we need to increase that, okay? So we don't design to the limit, and also we need to add a cover. So these rebars typically are placed in the center of the unit, so you add half of that as a cover below. So that's why, you know, we can have like 8 plus 8 plus 8, that's 24 inches, that's, you know, 3 units, plus 7.63, that's another one, because here, you know, this is the bottom of it, there's no mortar. And then the cover is 7.63. Now here, one thing that's important here is the 8 plus 8 plus 8, not 7.63. Now, why is that? This is important. Typically the thickness of the joint is 3/8 of an inch. So 7 and 5/8 plus 3/8, that's 8 inches. Okay, so one block plus a joint is equal 8 inches. So that's why that calculation is shown here. So estimate the amount of reinforcement, divide the moment by F sub S JD. We have everything. So it's 0.389 inch square. That's tool number 4. Okay. Then we can check the design here, meaning that, you know, use the correct row and then find the moment. It's 330 kip inch greater than the load. And then find the stress in the masonry. So it comes to be 537 PSI. It's less than the allowable. Okay, it's very simple. So that's how we use that reinforced masonry in ASD. Shear design of reinforced masonry. So we did talk about shear design before in unreinforced. So here we have, you know, we have rebars. So you can see we have a moment, we have a T, that's for the rebar, we have compression, and then we have the calculated shear stress is V divided by BD. Now the difference is, the difference here is for the calculated one, for unreinforced masonry is VQ divided by IB, which we calculated as 3/2 V/A. right? For rectangular cross section. Here it's different. We just use V divided by BD for reinforced masonry. So we have another material in this case, and we do not consider, the whole we have to consider the reinforcement that we have in the section. So that's the main reference. Instead of 3/2 V over A, it's V over A, V over BD. Okay, and here it is. That's how it's given in the code. Okay. So the allowable shear is the allowable shear is given as such. For reinforced masonry, we have FV. This is equal to F sub VM plus F sub VS. F sub VM, this is the shear strength of the masonry, the allowable shear stress in the masonry, and V sub S is the allowable shear stress in steel, multiplied by gamma sub V. So by the way, all these notations, they are all defined in chapter 2 of the code. Okay, chapter 2, you have everything, any notation that you see in the body of the code, you can go to chapter 2 and see that. This is multiplied by gamma sub G. Gamma sub G has been introduced actually in the last 2 cycles, the 2013 and after. This is a factor that accounts for the partially grouted shear walls. Okay, so if it's partially grouted, we use 0.75. If it's fully grouted, we use 1. Okay, so so that's why it's important, and it was overestimated before, sorry. So if it's partially grouted, we have to reduce that. So now this F sub V that we calculate here cannot exceed 3 times square root F prime M, F M over V times dV. dV is the depth that's used for shear, which is from the compressive phase to the reinforcement, less than 2.5. And if M over VD V is greater than 1, then the V in equation 825 cannot exceed 2 times square root F prime M times gamma sub G. The reason for this is to prevent any crushing failure and compression due to shear in the wall. So that's why we have these limits. So as you can see, this is less or equal than 0.25. This is greater or equal than 1. Okay, anything in between, we can do interpolation. Okay. Now, of course, if we are designing, so if F sub VM is given in this equation here, okay, because here we have 2 components, the masonry and the steel. So F sub VM is given in this equation. Now this is for special walls. Special walls are used in high seismic. So we may actually, we'll talk about that at the end. We may have like special masonry walls, so that are used for high seismic applications. So if it's so, we use this application. For all other walls, we use this. So this, for the special walls, as you can see, we use 1/4. So we don't give much, we don't rely on much capacity from the masonry for special masonry walls. But for other walls, we use half. Okay, and we also take advantage of any axial loads that we have, because if we have axial load, that will increase the capacity in shear. Okay, and F sub VS is equal to 0.5 times A sub V, F sub S, D sub V over the net shear area times the spacing between the shear reinforcement. Okay, everything is defined here, which I just talked about. Okay, so provide shear reinforcement to resist FV minus F sub VM. So we calculate the shear stress, and then if this is greater than the masonry, then we subtract the part that resisted by the masonry, and that's what's left need to be resisted by the steel. Okay, so here it is, F sub Vs, if V minus if Vm, then we can find the required area of steel and the spacing, just like concrete. So we say, okay, the spacing or the rebars need to be number 3. Then we can find the spacing from this equation, okay? Or we can say we need the, the spacing to be 16 inches, depending on the size of the block, for example. Then we can determine, the rebar area. But typically set the rebar area and find the spacing, just like concrete, okay? So shear reinforcement shall be provided parallel to the direction of the applied shear, right? So if the shear is vertical, so it has to be applied like this. In a shear wall, for example, the shear is horizontal, then we apply it at the joints. Spacing of shear reinforcement shall not exceed the lesser of d over 2 or 48 inches. That's the maximum has to be d over 2 or 48 inches. Okay. Now, also reinforcement shall be provided perpendicular to the shear reinforcement and shall be at least equal to 1/3 of that. So if we have shear reinforcement, especially in shear walls, if we have shear reinforcement, we have to have vertical reinforcement, at least perpendicular to it, that's equal to at least 1/3 of that. And we have also some prescriptive requirements that we'll talk about towards the end for the walls in masonry, for walls in high seismic, okay? Okay, so design for shear force is at a distance d over 2 from the face of the support. That's if we know, of course, to the face of the support, if not from the centroid of the supported element. This is similar to concrete. So in the case of cantilever, this is the maximum shear that should be used at that fixed end. Okay. Axial load capacity, for reinforced, if you recall, for unreinforced, we just had the masonry. That was 0.25 F prime M times the net area times what's in the brackets, if you recall. For H over R less or equal than 99. Here, we do have reinforcement, so we have to include that in the capacity. So we have the 0.25 F prime M times the net area, in which we need to subtract the area of steel, just like concrete, and then add to it 0.65 AST times allowable stress of the steel, multiplied the slenderness effect here, okay? If H over R is greater than 99, then we have to use this equation. Okay. Combined axial and bending for ASD, that's what we have. So this is the axial load, this is the moment. Here we have reinforcement at the center of the wall. Here we have compression on this face, that's the green part of the wall. So the stresses here due to bending is F sub B. Here we have F sub S. So the K, D, and JD that we talked about before in the case of the beam, they all apply, okay? Except that here we don't care about FT in unreinforced. We don't care about it. This is ignored completely. We have reinforcement now, so all the tension is taken by the reinforcement. That's the difference from the unreinforced, okay? So in the case of compression, combined, in the case of compression phase, so we have the same relationship applies here, okay? And in the case of tension, we have we have two conditions that need to be satisfied. So we have this condition that need to be satisfied, and the other condition is that the total axial load plus F sub B, these are the actual load stresses, has to be less or equal than 0.45 F prime M, okay, provided that F sub A is less than the capacity. So there are two conditions for the ASD reinforced masonry case that we need to check, okay? But we don't have the one that with the F sub T, okay? So that's given in this section. Okay, so in lieu of this approximate code equations, so you can use what we discussed using these checks, these two checks for combined loading. You can construct an interaction diagram showing the axial load in the vertical axis, and then the bending flexure in the horizontal axis, and then we have the balance point here. So if you do that, then you can you can check your load if it's within the interaction diagram or not. And this is something that we know also from concrete. Now the interaction diagram can be, of course, built manually, by hand, and we'll talk about this. Or it could be, you can create a spreadsheet that will create the interaction diagram. Once you have that, you can just use your loads to compare with it. Okay, so the general assumptions here, they are the same that we looked at before for the plane section remains flat section and the linear stress and strain diagrams that we talked about before. Okay, now let's talk about strength design for reinforced masonry. Now, this is important because in some areas like California, for example, you have to use reinforced masonry. That's number one. For seismic application, you have to use strength design, not ASD. Okay, so that's important. Okay, for that we use the ASCE 7-lot combinations for strength design. So everything is defined here for these load combinations. Now, the best way to cover strength design of masonry is to think of concrete. Okay, it's very similar. In fact, the concept of the masonry historically was designed as ASD, but during the last maybe two couple of decades, 2 decades, the strength design was developed. It's very similar to concrete. So you look at the stress distribution, strain distribution here. This is something that you are familiar with. So we assume, so we have epsilon sub mu, that's the ultimate compressive strain in the masonry. This is equal to 0.003, which is similar to concrete, but we use something else for masonry, as we will see. And here the stress distribution is like this rectangular block, which we used in concrete, that Whitney block, right, equivalent to it. So that is 0.80 F prime M. We use typically 0.85 F prime C in concrete. The depth beta 1 times C, we have the same thing in concrete. Beta 1 changes in concrete. Here we have 0.8 times C. It's a constant value. In concrete, it changes because of the strength of the concrete, F prime C. Here, it's a constant value, 0.8 C. Okay, and then T is T, and as you can see, Fy. Now we use Fy because we assume the steel will yield, unlike F sub S in the unreinforced. The strain in the masonry is 0.0, in the concrete block masonry is 0.0025 instead of 0.003 in concrete. In clay masonry is 0.0035. Okay, the tension reinforcement is to be is assumed to yield, and because the axial load is 0, now thinking about a beam, the flexural capacity depends on these two forces, the steel and the masonry. Okay, so that's what we have here. Okay, so we have the resultant in the masonry, 0.8 F prime M times 0.8 C times B. This is similar to concrete, right? T equals A sub S times Fy. the moment capacity is equal to ASFY D minus beta 1C over 2. We all know this equation from concrete, correct? So that makes it simple to understand and to follow and to use. And I recommend actually that. Using the strength design, not the ASD design, but both are allowed in the code. Um, so if we equate the tension to compression, okay, we can find, sorry, the depth of the compression block, that's beta 1C, right? That's the A distance that we use in concrete, okay? So if we use rho as the reinforcement ratio, AS over BD, and then we use omega as the reinforcement index, which is rho times Fy divided by F sub m. So just, make, these substitutions, you will get to this nominal moment equation, which is a function of the dimensions, the strength, and the reinforcement index. Okay, this is again similar to concrete. If you ask me, some people are used to this because it has its uses. If you ask me, I will just use this one, the first one, because this depends on this free body diagram, which we all can draw and use to find the capacity. Okay, so that's what it is. Now, of course, to make things simpler, this lever arm between the tension and the compression could be equal to 0. Well, I mean, we can start an assumption that's equal to 0.9 D. Okay, 0.9 D. Of course, this is useful to estimate like the depth of the member in case we don't know it, if we are designing, right? For design. If when I say design, this means finding dimensions. If the dimensions are given, the reinforcement is given, then we are doing analysis, okay? So now, one thing that's important that which was not before in masonry code is reinforcement ratio. Is reinforcement limits, minimum, maximum, like we have in concrete. For now in ASD we don't have that. In strength design we have that, and that's very important for the behavior of the beam. Think of concrete. Why do we need the minimum reinforcement ratio, and why do we need the maximum reinforcement ratio? Okay, that of course affect the behavior of the member. What will crack first, what will yield. Is it over reinforced? Is it under reinforced? Is it ductile? Is it brittle? So this is very important and has been developed and incorporated into the strength design. Now, the same thing here, we have a balance condition. So for the balance condition, again, we just assume that the strain in the masonry has reached at the same time the yield strain has been reached in the reinforcement. Okay, so we can use that, and then we can determine the balanced condition. And of course, for the balanced condition, we have that depth is different, right? That depth typically is higher than what it should be in an actual behavior of a reinforced concrete beam or masonry. Okay, so this is higher typically, and that's found from the relationships. As you can see, for reaching the strain in masonry, the maximum strain in masonry and the yield strain in steel, okay, C divided by D minus C, exactly like reinforced concrete. Then we can find C, the depth of the compression block for the balance condition, from the strains that we have here and the depth of the member. So using the balance conditions, we can use using the equilibrium condition here, we can determine the balanced reinforcement ratio here. So this is the balanced reinforcement ratio. Depends on F prime M, depends on Fy for the steel. Okay, it depends on beta 1, which is in this case for masonry 0.8. It depends on the strains. If it's concrete block, 0.0025. And then if it's 60 ksi, epsilon y can be calculated, right? 60 divided by 29,000. And if it's a clay masonry, of course, you can use 0.0035. Now, once we have row balance, we can select a row that's less than that. So that makes it easier, okay? So the shear strength of the walls is the shear strength of the masonry in strength design is given now in V, in forces, not in stresses, F sub V, like we had before. And that's typically the case for strength design, right? We find P sub N, M sub N, V sub N, right? Not stresses. So it's the same concept like we talked about before, except that here we have forces, and also here the limits are different because this is strength design. So we go beyond the allowable stresses and beyond uh, 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 the yield point, right? So that's why you have 6 times A and V times square root F prime M, everything times gamma sub G. And this is less or equal than 4 times A and V square root F prime M, everything times gamma sub G, okay? Anything in between, you can do interpolation. And that's the same thing here for the nominal shear strength in masonry as a force, okay? As a force in kips or in pounds. This is, that's what we need to use. And then V sub NS, okay, the contribution of the shear reinforcement for the contribution of the shear reinforcement the contribution of reinforcement in the shear resistance is given by this equation, which is similar to what we had before, except that this is a force again. Okay. Now, steps in strength design for reinforced concrete beams and lintels. Now, this is most common reinforced concrete masonry beam is a lintel. So if we're talking about the beam, we're talking about lintels over openings. So those are over openings, typically reinforced. The shear design, okay, calculate the shear design and compare it with the corresponding resistance. Revise the lintel for the depth. So in lintel design, if we can avoid using reinforcement and use depth, so increase the depth, that is actually better. Because typically above openings, we have enough depth compared to the span of those openings. So we can check if the depth is enough for the shear resistance. So that will determine the depth of the lintel that we need to use in our design. If it's not, then we can use shear reinforcement. For the flexural design, calculate the design moment, calculate the required flexural reinforcement, and check, again, this is using the rectangular block, compression block in the masonry that we showed in the free body diagram before. Check if it's within the maximum and the minimum reinforcement limitation. So this is an example of lintels, like over opening. So you can see, so here we have like 4 blocks, right? 4 blocks, if each one is 8 inches with the mortar joint, so that's 32 inches. That's a very deep member. So look at even to scale the depth compared to the opening itself. Okay, so this could be enough. And that's why we will end up maybe with the really minimum reinforcement in the lintel, maybe one rebar, or which is the minimum, by the way, 1 rebar or 2 rebars. Okay, we just talked about these. Okay. And okay, strength reduction factors. Okay, so we talked about load factors. Now we talked about, so we have Vn, we have Mn. So these are nominal stresses. So just like concrete, we have 5 factors for the reduction of the nominal strength to get the design strength. So those are given here. So if you have combination of flexural and axial loads, reinforced masonry is 0.9, unreinforced 0.6. If it's shear, for shear, 0.8. If it's bearing, 0.6. Okay. And if we are talking about anchorage to masonry, which we are not covering today, but for anchors, for masonry breakout, crushing, for anchor pullout, we have these 5 factors. Okay, those are given in chapter 9, uh, which is again strength design for which is strength design for reinforced masonry. Okay. Okay, then we have modulus of rupture. Okay, so the modulus of rupture, that's actually the tensile capacity of the masonry. In the case of unreinforced masonry, that's designed according to strength design. Okay, we use F sub R, that's the modulus of rupture. So you can see the values here, they're much higher than the value that we saw in chapter 8 for the allowable stress design. So here you can see, for example, we looked at this value before, that's 64. That's hollow unit, ungrouted, type N mortar, that's 64. That was 25 in ASD. So if we are designing unreinforced using strength design, this is the table that we need to use. Okay. Now for beam design, that's given in section 9.3.4.2, which defines what a beam is, in which typically the factor, we don't have axial load in it, so it's less than 5% of the net area multiplied by the compressive strength of the masonry. We have also another requirement which has to do with the nominal flexural strength of the beam shall not be less than 1.3 times the cracking moment. Okay. Now the cracking moment is determined from F sub R, the modulus of rupture. The modulus of rupture multiplied by the section modulus, that will give us the cracking moment. Okay. Okay, so here we have some other requirements for the beams that are related to the reinforcement also. So the transverse reinforcement shall be single bar with 180-degree hook at each end. So if we use shear reinforcement, so it should be 1 bar with 180-degree hook. Transverse reinforcement shall be hooked around the longitudinal reinforcement. Minimum area of transverse reinforcement is 0.0007 times B times D, the effective depth for the shear. And then the first transverse bar shall not be located more than 1/4 of the beam depth from the end. The maximum spacing shall not exceed 1/2 the depth of the beam, or 48 inches. This is similar to what we shown before. Okay. Now the beam shall be fully grouted. If it's a lintel, the beam should be fully grouted, not partially grouted. That partially grouted or hollow, that's for walls only. Okay. Now this covers the protection of the reinforcement and metal accessories. These are requirements for the cover. What is the cover? The minimum cover required for the masonry to protect the reinforcement, so that's similar to concrete. So we have the provisions given in section 6.1.4. Okay. Now looking at the design strength of reinforced concrete, reinforced masonry bearing walls. So typically what we have is something like that. So we have part of a masonry wall like this. So we have a rebar in one of the units, in one of the cells. Not in every cell. It is possible that we have it in every cell. Okay, but it's that will be, of course, that will give a big capacity, which is done sometimes. So if you have a multi-story reinforced masonry building, as the load accumulates, so when you get to the first story, you may need 1 rebar every cell, sometimes 2 rebars every cell. Okay. So here, okay, this shows the thickness of the wall, that's T, and this shows the effective width for 1 rebar. That's 6 times T, so 3T from each side. So when we take a section to design it, okay, that's what we use, 6T by T with the rebar in the middle cell. Okay. So that's shown here. So effective compressive width per rebar. Now it's this depends on the center to center bar spacing. Okay, so if we have one every cell or every two cells, okay, it's 24 inches. So it's a multiple of 8, typically 8-inch, 16-inch, 24, 32, etc. And then it's 6 times multiplied the nominal wall thickness, which we just talked about, or 72 inches. So we should go with the smaller one, okay? So using the strength approach, we seek to construct an interaction diagram. So again, that will be the best way to design walls. Just use an interaction diagram, which can be done by hand or by spreadsheet. Okay. So this is similar to what we have shown before, except that here we have P sub n, that's the nominal axial force. Here we have M sub n, that's the nominal moment here. This is the balance point. So we need, again, check P and M and see where we are, if we are within the interaction diagram or not. Okay. So to construct the interaction diagram, we can talk about some background related to that. So we have a pure compression case. This is equal to this equation without any consideration to stability. Okay, so that's the pure compression case. Okay, so it's the same equation that we showed before, except there is the stability factor that was in the, here you can see it in the brackets on the left hand side, without it. Okay, without that. So that's this here, the one at the top of the vertical axis. And then for the pure flexure, which is on the horizontal axis, that's the pure flexure point here. Okay, that is done using okay, we have the reinforcement and then the reinforcement index, or so M sub n is equal to, ignore any axial load. So the axial load is 0. So A sub S Fy times D minus beta 1 C over 2, right? Pure bending. We find that, and then we locate it at the horizontal axis. So now we have 2 points. We have the pure compression, we have the pure flexure. Now we need, so if we are doing it by hand, we need one more point, which is, by the way, a conservative approach. We can find the balance point and then connect between them. And this is accurate enough, but a little bit conservative. If you need one that's more conservative, then you need to develop a spreadsheet, because you need more points. You need to take more points to create the curve. So it's not P sub 0, Mn. So you have to take P and P, you have to take the balance point, you have to take a point below the balance point, after the balance point, to construct the entire interaction diagram. This can be done using an Excel sheet. So the balance point, we need to define that. We showed before how we can calculate this, right? So using the strain diagram, so the steel will yield at the same time when the strain in the masonry is reached. Okay, so we can calculate C, and then we can use equilibrium. So in the balance point, if we go back to this is the balance point. The balance point, we have axial load component, we have a moment component. Again, we did that in concrete also. So so here, based on the free body diagram here, so we have this tension force, we have that compression force, and we have also the axial load. So the tension is AS times Fy, the compression is 0.8 F prime M beta 1 C times B, and then the axial load P sub n is C minus T, compression minus tension. Okay, then we can write this equation. That's Mn. Okay, that's Mn. Take the moment about 1 point, find the other one. Okay, from here, from this free body diagram. So now we have Pn and Mn. That's 1 point. using Pn and Mn, that gives me this balance point. Okay, using the strains that will, for the masonry and the steel, that will be reached at the same time. Okay, so having this, we can create the interaction diagram, which looks like this. Okay, so this is an example where we have 8-inch CMU wall, F prime M 1500. We have number 5 at 48 inches placed in the center of the wall. Compute the interaction diagram. So using this procedure that we just described here, this is what we have. So this is calculating 3 points, and it's accurate enough. It's accurate enough, okay? So now you can look at whatever P and M you have, and if it falls within this, then it's okay. If it's outside, then you have to revise your design. So here you can see you write at the top of it. So anybody who's using it, for what data this has been done, 8-inch solid CMU wall, if prime is 1500, and then number 5, the reinforcement is number 5 at 58. Okay. So if you want to calculate the strength, the interaction diagram using the spreadsheet, so we need to calculate the position of the neutral axis corresponding to the balance point, like we did before. So this equation, now we have seen it, several times. Okay, so this is the strain diagram and the free body diagram for the balance condition. Now for the C values, that's less than, see, now that's what we said before. We need to look at cases that are away from the balance point, before and after. So we said for the balance point, C value would be large. So we need to look at values that are less and values that are bigger. So for values of C less than the balance point, the steel will yield before the masonry, and that's what we want. Okay. Now, if C is greater than, that's undesirable condition. Okay. So as here, so you see we have a smaller compression block. So that's what we need. So we need to look at C values less than that, and then do the same calculations like these here. We have obtained this, we have obtained Mn, and now here. So we use a different C value, right? So now this is the C value here. C value here. We use something that's less than what we obtained for the balance condition, okay? Then find a new Pn, which is C minus T, and find a new Mn and plot it in the interaction diagram. So you can do that. So you can list 10 C values in the Excel sheet and just calculate them, using these two equations, okay? Okay, so this is like, so you go from a range that's like this, see the depth of the compression block, to something like that, before and after, okay? And then do all here you have all the procedure, how to calculate that. And okay, we know beta 1 is 0.8, okay, A is 0.8 C, that's what you get. See, this is more accurate interaction diagram that you can create from the equations that we just added here. Okay, and here it is. So that's see, example of a spreadsheet for calculating strength moment axial force interaction diagram. So you have the specified thickness, epsilon M sub U, F prime M, Fy, E sub S, D, etc. You can calculate everything here. These are the C values that I talked about. Okay, starting from the full thickness all the way down. Okay, but here you have to be careful which equations you need to use before the balance, after the balance. You can go back to the slides and use those. Of course, first you have to find the balance point, which is shown here. Balanced points controlled by steel. So that's actually above those, you will have, so this is the balance point actually here, okay? And then the C values that are actually less than that here, below that, those are controlled by steel. Above that, controlled by masonry, okay? Now, strength design for shear walls. Again, the concept of a shear wall is very similar to what we have done now, except that the force is now in the plane of the wall, and we may have more reinforcement, vertical reinforcement in the wall that we need to consider for the shear wall. So the loads that are there, they are the gravity load, including the self-weight, plus whatever load that's coming from the roof or the floor. Moments and shear forces, they are in the plane. Now they are in the plane of the wall. So that's what we have, right? We have axial force, we have shear load. Now the flexural capacity is determined exactly the same way. But here we have, we have multiple rebars that extend up, that we need to take those into consideration. The shear capacity is done exactly the same way. Now, in this case here, we have, it's not only the width of the wall that's used for the shear capacity, it's the entire length of the wall. Now look at the shear force, right? So this is the length that's parallel to the shear force. So we need that to calculate the shear capacity. In that case, you look at the strength of the masonry, which would be a lot, depending on the length of the wall. And also between the joints, if masonry is needed, if reinforcement is needed, then we can include that under V sub SN, okay? That's a shear reinforcement for a shear wall, which is between the joints, okay? So that's what we will have. So this is the shear force. Here we have, this is the reinforcement, which is at the joints. And that's, for example, that's D sub V from the compression phase to this value, which would give us 45 degree failure, okay? And this is an approximate value for dV. So again, 45 degree the failure, similar to concrete. That's what we assume in ACI 318 as well. Okay. And then V sub NS is calculated, using whatever shear reinforcement that we have, multiplied by F sub Y multiplied by N, which is D sub V divided by the spacing of the reinforcement. Okay. Now here, all reinforcement crossing the failure surface may not yield. Okay, so we don't know if all the reinforcement will yield. For both of these reasons, which is the actual failure surface may be inclined at a larger angle with respect to the axis of the wall. Okay, and also not all the reinforcement may yield. We may have, we can reduce the contribution of the steel to the steel resistance. We can use this equation and reduce its contribution, okay, by half. So here we have the same thing like that we discussed before, okay, for the contribution of the masonry, okay. And this is in the same equation that we just discussed, which is in the code equation 9-25. Okay, so now here we have, again, for shear walls also, an interaction diagram, because we have axial load. Typically we have moment. We have axial load and the moment is due to the shear force. We can also develop an interaction diagram and look at the forces that we have. Now we have so seismic, if we're going to talk about seismic, that will of course require, that's a topic by itself, but we do have some prescriptive seismic design requirements for masonry shear walls. First of all, depends, we have to classify if this is an ordinary wall or if it's an intermediate or if it's special. So that depends on the seismic design category that you are in. So going to the last slide here. So if you are in seismic design category A, none. If you are in B, so shear wall must be at least detailed as plain shear walls. If you are in C, then you do have some requirements with some also reinforcement, minimum reinforcement requirements. If you are in seismic design category D, then that's a special wall. Then you have also requirements, including, for example, fully grouted type S or type M mortar. So these are some of the prescriptive requirements that you have to use depending on the seismic design category. Okay, so for that, go back. So for ordinary plain, there are no prescriptive requirements. If it's a detailed plain or ordinary reinforced, you do have some prescriptive requirements, such as vertical reinforcement at least 0.2 inch square at corners, within 16 inch of each side of the opening, within 8 inch of each end of the wall, maximum spacing of 120 inches. Okay, that's an ordinary wall. Horizontal reinforcement of one of the following: 2 longitudinal W1.7 wire joint for reinforcement, spaced at not more than 16 inch on center, at least 0.2 inch square, etc. So we have those prescriptive requirements. If it's an intermediate reinforced masonry shear wall, we do have also other requirements. Now, how do you know which one is allowed, which one is not allowed? So we do have the seismic design category, and also we need to go to ASCE 7 in a table, I think 12.2-1, and see in which seismic design category we are allowed to use detailed, plain, ordinary, intermediate, and special. Okay, so here these are the prescriptive requirements for a special reinforced wall as well. Okay, so here, as you can see, we have minimum requirements for row sub V, that's the vertical reinforcement in the wall, and row sub H, that's the horizontal reinforcement of the wall, and a combination of both. Okay, in addition to whatever design that needs to be done, by the way, it's not only these. It's not only these that's required for the special reinforced masonry shear wall. Okay, so with this, I conclude. I will be glad to take any questions. Any questions? Okay, if there are no questions, I will end it here. And feel free to email me with any questions that you may have, and I'll be glad to answer them. Thank you.